Like we've got an infinite Google Hangouts. I'm Dan Lurie, graduate student at UC Berkeley, and I'm going to be presenting a very quick introduction to using NiBabel to read in nifty files, neuroimaging MRI files, so that you can work with them in Python. This is part of the Brainhacking 101 course for Brainhack Americas. So let's get started. So what we've got right here is just a Jupyter notebook. And if you're not familiar with Jupyter or IPython notebooks, I really recommend you take a look at them because they're a great way to kind of experiment and make sure that you understand what's going on and keep your work so they don't have to keep refreshing things in the terminal. So first we'll import our libraries. And we'll see, this is NiBabel 101. And the first thing I want to do is just go a little bit through what NIFTY is. NIFTY, it stands for the Neuroinformatics something. Forgot, it's very confusing. Neuroimaging Informatics Technology Initiative. That's right, I always just think of it as NIFTY. Anyway, it's a file format that is pretty ubiquitous in neuroimaging, especially for fMRI, and is probably the easiest file format to read data from when you're working with fMRI images in Python. There are things like DIPOMs or analyzed formats where you have header and image files, but that's a little bit difficult to keep track of, and NIFTY keeps them all in one place. So I've put some links here in this notebook, which I've put up on the GitHub, if you want to know a little bit more about NIFTY, and also specifically some things about the parts of them and about image orientations, which is really crucial to know because as with all MRI data, it's very difficult to keep track and sometimes impossible to keep perfect track of which way the image is oriented in terms of right, left, up, down, and things like that. But in terms of a NIFTY image, there are three main parts. You have the header, which contains metadata about the image, and that's one of the nice things that it carries over from DICOM in the sense that you can get some, but not all of that metadata information about the scan. So you can get the image dimensions, you can get what the data type is, for instance, the TR of the scan. It doesn't have all of the info of a DICOM header, but it has some. And something to keep in mind is that because different things can read and write to NIFTYs, sometimes the headers aren't reliable. So if you're going to be needing that information, it's usually good to go back to the original DICOMs. If you are working with DICOMs and you don't have NIFTYs, I recommend using this great software from Chris Warden. It's MRI DCM2NI, which is very good at just taking in your DICOMs and spitting out NIFTYs. It'll also anonymize them if you need to do skull stripping, or at least try to strip off the face. So we've got our header. The next part is an affine. So an affine transformation is just a matrix that defines the transform between what we call data space or image space and world space. So the difference is, whereas you might be, 4 voxels in to the image, you might want to know, well, how many millimeters in on the x-axis am I? And that differs between whether you're in TALORAC space or MNI space or a different image space. And so this gives the translation between millimeters coordinates, X, Y, Z, and voxel coordinates. And there's a great page on the NiBabel documentation to go through that. There's also a good blog post by Chris Gorgolewski from NiPipe to talk about how a very easy way in code to translate from one set of coordinates to another. And then there's what we usually want to try and get out when we're using NiBabel, which is to get the data. The data usually comes in the form of a multi-dimensional array. So you've got X, Y, Z for your 3D volume, and then you have T if you have a 4D volume, so volumes over time. So with NiBabel, reading images is really quite easy. There's 2 parts. You want to load the image and then get the data. So in terms of loading the image, this kind of loads an image object, which is not the actual data, and it lets you learn some things about the image without having to load it all into memory, which can be an issue, especially if you're working with multiband data or very long scans that take up a lot of memory. So we go EPI image, and we use nib.load, and then just the path to the image. So once we see that, we can see what the image shape is. So we want to see what the shape of the image is. We say, okay, so it's 91 by 109 by 91, and there's 120. So 120 means that there's 120 volumes, and the first 3 numbers are the X, Y, and Z dimensions, so in the 3D volumes. So time is almost always on the last axis, depending on what kind of scripts you're using. Once you have the data, it's often necessary to flip it around and do it and make it so that time is the first axis. But for now, we're going to keep it the last axis. Another thing we might be interested in is what kind of data is this? Is it, is it float data? Is it just integer data? So you can see that this is, I think that's little endian 64-bit floating point data. And so that's useful to know if we think we might want to load it into memory, because that'll impact how much space this takes up in memory. So loading the data doesn't actually get you access to the data directly. It has what's called a proxy object that you can pull from, and to pull that proxy object, we run the get data function. So we just take our image objects and run the get data function on it. And so we go get data, and so that's read in, and now we have our data. And you can see it goes pretty quickly with this. This is 120 volumes of 2 by 2 by 2 millimeter 2 by 2 by 2 millimeter MRI data. So it's not a whole lot of data. If you say you were working with 2 by 2 by 2 millimeter data for 900 volumes, if you had a multi-band scan that was like 10 minutes long, that would be a lot more data, and it might take a couple of minutes to read into memory. So that's something to keep in mind. So what we can do is let's check that indeed that we have the same shape for our data as we did reported from the image object. So we can do EPI data shape and see that we have the same shape here reported by the image objects as we do in our actual data. And we can look and see that type EPI data. See that this is a NumPy memory map, which means that it is trying to NiBabel will try when it can to use a memory map so that you don't actually have to read it all into memory. But we can see that this is a NumPy array, whereas this is a NiBabel object. So we go type image NiBabel object. So now that we've got our data, it depends what you want to do with it, but often the first thing you want to do is to make it, reshape it into dimensions that are a little bit easier to work with, because working over 4 different axes to try and index the data you want can be tricky. So often what you'll want to do is to reshape it into an n voxels by n volumes. So you create a vector of all the voxels in a volume, and then you just have another axis over which the volumes, right? So what we can do is we can use the normal standard NumPy reshape command. And so we'll take the product of the first 3 dimensions. So we'll just multiply that. That's the volume, length times width times height. And -1 means we're going to ignore the last axis on this, the last index on this array. And then we're going to say that we want it to be the product of the first 3 minus the last index, which is the number of volumes. And so then we'll see that once we do that, it takes a while to think because it has to ravel all of those volumes into vectors. And you can see now that we have 902,000 by 120. And so this is easier to do because in most cases you don't actually need the 3D structure of the volume to be able to do analysis on it as long as they're lined up. So you can do reshaping like that. But what is often better to do is to use a brain mask. And so a brain mask we can take a look at. We'll load in our mask. And let's take a look at what it looks like. So here on the left, we have our EPI image plotted. So this is just a slice from the EPI image. And you can see that there's these continuously varying voxel intensities. This is a pre-processed image. So a lot of the white gray matter contrast is gone. And we've z-scored it because hopefully we've gotten rid of a lot of the physiological noise and just have the bold data, which is the fMRI data. And on the right, we have the brain mask for the same subject. And you can see that they line up pretty well because it was calculated from this file. And the goal is, you see all these gray, this flat gray expanse in the background. Those are outside the brain, and we don't want to deal with them. And specifically, we don't want to have them impact our analysis. So when you're doing things like taking a mean or a median, that's going to, if there's a whole lot of zeros in your array, that's going to impact your analysis and screw up the value you're getting out. And so what we do is we mask these out and get a vector for each volume that is only the voxels that we're interested in inside the brain. And so what a mask is simply just a image of exactly the same dimensions as your data image, except instead of having these continuously varying voxel intensities, it just has ones and zeros. So ones show up as white here, zeros show up as black. Any voxel that has a 1, we're going to keep that data, and any voxel that has a 0 or a false, we can think of them as true as false, we're going to exclude that data. And what we're actually doing in practical terms is we're using the image, the mask image, as an index. We're indexing the array for our data image, and we're just pulling them out. So if you look at, so we've already loaded our mask, so I can actually get rid of this. And we see, okay, so we're going to make sure that our mask is Boolean. That means we want it to be only ones or zeros, only true or false. Because if it's not, then when we try and index it, it's going to get confused. So we made sure that it's Boolean. Now we're going to mask the data array, which is as simple as using an index. So the same way I would try and, I would put a 0 here if I wanted the first element of the EPI data. I'm going to put the mask data here, and that's going to mask the data. And at the same time, for that thing for a bit, it's going to reshape our data from the 4D into this 2D, which is the same, which is essentially the same thing as reshaping, except now instead of 902,000 voxels, we've only got 316,000 voxels because we've excluded all of these uninteresting 0 voxels outside the brain that we don't need. So that's kind of a nice thing about masking, is when it's done, you get it into this n voxels by n volumes format, which is easier to work with. So now that we've got our array, that the data in a format we want to work with, so maybe what we want to do is, because we're working with a time series image, we've got a 4D image and fMRI image over time. So whereas each volume is a picture of the brain taken over time, let's say we want to take the standard deviation of that over time. So we want to see which are the most varying voxels over time. So that might tell us where the noise is, or if we've cleaned up our data well, that might tell us where the signal is. So we're going to do a standard NumPy operation. Once you've extracted the data from NiBabel, it is just a NumPy multidimensional array. So you can do anything with that as you would with a normal ND array. So we'll take the standard deviation, we'll do it over the first axis, or rather the second axis, because Python is 0 indexed, and that'll give us the standard deviation over time. And so we'll see it's collapsed over time, so we no longer have this 120 here. We've collapsed over the volumes, but we still have the same number of voxels within the brain. So now we've got that, the question kind of is, well, how do we get it back into something that we can work with outside of Python, or something that we can view? Because right now, if we tried to view this, it's just a one-dimensional vector, and it's not lined up in terms of how the voxels actually sit in the brain. So to do this, it's almost as easy as masking the image in the first place. And so what we do is we create an empty array of zeros that's the same shape as our template, or as the image that we're going to try and create. So we're going to use the mask shape, but we're going to make sure that the data type for this array is the same as the data we're feeding into it. So D type equals standard EPI masked. And then we'll check this and we'll say, okay, great, this is 90 by 109 by 91, which is the same shape as one of the volumes in our EPI data. So we're good on that. Then all we do is we mask the new empty array with our mask. So that means that this object right here is the same voxels as in this object right here. And so we're just assigning this data that we've calculated, our standard deviation image, to this empty image. But because we're only writing to the voxels inside the mask, we get to add this to our 0 array, which means that we're regaining all of these voxels outside the brain, which are necessary in order to have this nice, this cubic image. So I'll run this, and now we can view it. So now we can see, whereas compared to this, where there's a lot of noise, or rather there's a lot of variation across the image in terms of voxel intensity at any given volume here, when we collapse across time, we can start seeing the pattern of the brain. We can see the white and the gray matter. We can see maybe in front and in back, we've got noisier data, and so that's useful. But it can show that this is something that you might want to do. You'll probably want to do something a little bit more complicated. If you're reading data into Python, maybe you want to do a PCA on a time series or things like that. But the principles are all the same. Once you have the data in an ND array, you can do whatever you'd like. So now that we have this image, we want to write it out so that we can view it in something like FSL, or we can run it through SPM or AFNI or something like that. So writing is a little bit more difficult than reading in because we have to construct an image object, but we can use the images we already have to do that. Because remember, we have 3 parts to a nifty image. We have the header, and we have the affine, and we have the data. So we already have the data. We've calculated that as our standard deviation image. The affine and the header we need to create because that's going to tell the software that read this file about how to translate the coordinates and information about the file. What I generally do, and what I've seen a lot of people do, is you take the header and affine from an existing file. So what we're going to do here is we'll take the mask image, and because we're working on the image, we can use the get header and the get affine function, which are the equivalent of the get data function, and we can run them. And so now we've got our header and our affine. But because we've changed the data type, whereas the mask was just 1s and 0s, it didn't need to be a float image, or it didn't need to be an int32 image if we're trying to save space. It was probably like an int8 or an int16. But our new data is decidedly larger variation of values in that, so we want more space to code that. So we're going to take the unmasked data type, and we're going to get the unmasked data, which is now our SD image, and we'll say get this D type, and we're going to set the data type on the mask header. And so now we've done that, we can create the NiBabel nifty1 image. So this is an image object, the same as what we loaded in here. So this is also a nifty1 image object. And we're going to create it by saying here we're going to have the data, we're going to have the affine, and we'll have the header. And so we'll set this. Now we've got that. It's just as easy as using, saving a CSV out of pandas. You say, SD image, which is our image object, to file name. We give the path that we want to do. So okay, we've got that. So I've put that in, Dropbox talks NiBabel. So let me go to my browser, NiBabel 101. And say great. So I've got SD EPI image. Select that. Open in terminal. I go FSL view. And now we see that we have the image that we've calculated completely in Python. We've done all the analysis there, but we have it, and it's something that we can open up in a standard neuroimaging software. So that's NiBabel. I've put some links in this notebook, which is up on the GitHub. I recommend you read them or talk to people at your local events about the peculiarities of working with neuroimaging data if you haven't before. Orientation and kind of image coordinates are something that are a little bit tricky to get your head around to begin with, but usually you're able to kind of start working with it pretty quickly. I hope this was helpful. Enjoy hacking, and hopefully I'll see you around. Bye-bye.